Hello everyone, we are on page 12, so please turn to page 12 in your packets. We're going to be covering topics 6.7 and 6.8, and we're going to be looking at two ways where we can figure out what this change in energy, this enthalpy change, is for an entire reaction. Okay, there's two different ways we're going to go about doing that. Also, big reminder, please remember that watching the videos is not enough. You have to be taking notes with the videos. Okay, so you cannot just be watching the videos. You need to take the notes while you're watching the videos. All right, so I'm going to take this carbon dioxide molecule, okay, this CO2 molecule. Okay, so I'm going to take this CO2 molecule, and I'm going to have two of those. And I'm going to be turning them into products. But before I can make any products, we have to break old bonds. And we know that they're flying around. We know they're going to run into each other and they're going to knock these apart. But what's cool is that these bonds have to break. And I want you to notice something, that when I go to break this bond, they're held together. That they don't just fall apart by themselves. I have to pull them apart. I have to add energy in order to break a chemical bond. Okay, so if we're talking about breaking bonds, okay, breaking chemical bonds, that's an endothermic process. That energy has to be added before those bonds can be broken. So we have to add energy to break those bonds. Okay, so I added a whole bunch of energy to break those bonds. Try to keep them broken. And then we have to break those bonds. I have to add energy. All right, now, what's cool about this is after they're broken, we form new bonds, okay? And so we have probably 2 carbons that don't form bonds, and then 2 O2s would be my guess. And so I want you to listen to this. I'm going to set the carbons aside for a moment. And it might be, yeah, you can hear it. So when these form a bond, oh, that's quiet, it releases a sound. Okay? That if they get close together, they want to do that. They come together and we hear that noise. Same, it's not forming this bond, but we hear it really loud. Okay? That's an example of energy being released. So this might be a little counterintuitive to some of us, that when I want to break a chemical bond, I have to add energy. I have to add energy to break a chemical bond. But when chemical bonds are formed, energy is released. And for this example, it did it in the form of sound. We could hear it, right? So I have to add energy, and then energy is released when they come back together. So an exothermic process is bond formation. So breaking bonds is exothermic. I have to add energy, but energy is released when bonds are formed. Okay, so exothermic breaking bonds, well, let's do forming bonds. Energy is released when bonds are formed. Okay, now, if this chemical reaction was the same 2 things happening, meaning that I break apart this to make it ionic now, should be a sodium chloride. That's what this model usually is. So I break apart the sodium chloride. That took a certain amount of energy. If the exact same bond is reformed, it releases the same amount of energy. Okay? So if it takes 20 joules to break apart this bond, then it will release 20 joules when it comes back together. But what we don't know is that, like, the bonds that are broken are not always the same that are formed. So this exchange is not always equal. We can end up with a net positive or a net negative when it comes to energy, and that's how chemical reactions can be endothermic or exothermic. So back to the example that I had. Here's my 2 carbon dioxides, okay? And it takes energy to break these bonds apart. And like quite a bit of energy. It's like harder to pull those apart. So just for argument's sake, this is not the actual number, but let's just say 100. It took 100 kilojoules to break those apart, okay? And then, so like I had to add 100 kilojoules into the system in order to break those apart. Then when they formed, this one didn't bond again, so nothing was released there. But this one did. So after I break these apart, when this O2 forms, energy is released. Okay? So when this O2 forms, energy was released, but that was really quiet. There wasn't a lot of energy that was released. Like maybe there was only 20 kilojoules of energy that leaves. So then what is that reaction? Is it endothermic or is it exothermic, right? Like if we think about this for a second, this is my chemical reaction. CO2 turns into 2C and 2O2. Okay, great. And we had to add 100 kilojoules to break those bonds, and then it released 20 kilojoules. So instead of drawing those 2 arrows, we could instead say overall, I had to add 80 kilojoules, right? 80 kilojoules on, like, in total was lost from the surroundings that entered the system. Technically it was 100 and then they got 20 back, but overall 80 kilojoules went from the surroundings to the system. And so that would be that's an endothermic reaction. This would be a positive delta H of 80 kilojoules. Often we have these diagrams. So here's a different chemical reaction. So to break these bonds, the 1, 2, 3, 4 CH4 bonds. I'll do a loose dot structure on the next one. So it took 1, 2, 3, 4 carbon hydrogen bonds and 2 O2 double bonds. To break all of those bonds, it would take 2,684 kilojoules of energy to break all of those apart. Okay? And then we form these new bonds. It forms a double bond between a carbon and oxygen. That happens 2 times. And then it forms a single bond between oxygen and hydrogen, and that happens 4 times. 1, 2, 3, 4. And all of those bonds will release energy, and it releases 3,450 kilojoules of energy. Okay? So if we think about this system surroundings, okay, so I have this chemical reaction up above, reactants to products, and in order to break the bonds for the reactants, it cost me 2,648 kilojoules. And then when the products were formed, it released 3,450 kilojoules. Then what is like my net total to the surroundings? More was released than was entering. And so if I put these together, it's like saying overall, through this reaction, the surroundings is going to gain 802 kilojoules, or the system is going to lose 802 kilojoules. This is exothermic. Now, how could I get that number, right? Because I just subtracted the bigger one from the smaller one. But this is exothermic, so if I do a delta H, I would want it to be negative. And so what's cool is if you do the amount of energy, so like if you sum up all the energy of the bonds that we break, and you minus it from adding from all the energy that's released when bonds are formed, that will equal your delta H. And if it's negative, it'll be exothermic, and if it's positive, it will be endothermic. And so that's where we get this delta H for a reaction. If you add together, summation, add together all of the energy of the bonds broken, and you minus it from adding all together the energy that's released from bonds formed, then you'll figure out what the delta H is for the reaction. A really, really, really important part of this is drawing the Lewis dot structures, though. Like, the most common mistake that students make is they don't draw the Lewis dot structure, and then they miscount the number of bonds. So let me show you. We are going to take our reactants. Okay. And then we got our products over here. Okay, so it's a CH4. So I have a CH4. And if I look at this, I have a hydrogen or a carbon bonded to a hydrogen, right? This bond, and it happens 1, 2, 3, 4 times. So there's 4 of those. And then I have 2 O2s. So if you draw that Lewis dot structure, here's a single O2, but we need 2 O2s. And so for this guy, this oxygen double bonded to an oxygen, I'm going to break this double bond twice. So I need to consider all of those. I need to add all those together to get the energy of the reactants. Now, product side, we're going to form a carbon dioxide and then 2 water molecules. All right, great. So, oxygen double bonded to carbon. So we have this oxygen double bonded to carbon, but it happens 2 times inside of this molecule. So I have to consider 2 of those. And then for this guy, there is hydrogen bonded to oxygen, single bonded to oxygen, and this is 1, 2, 3, 4 times. Okay. Now, I have numbers for these different bonds right here, but before we do that, I want to lay out this summation, okay? So the sum of the bonds broken minus what's formed. So here's what's being broken. So I know delta H is going to equal the sum of the bonds broken. So I usually do brackets, and I'm going to show this is my number for carbon single bonded to hydrogen. Oh my goodness, sorry. Let's put that there. Okay, so this is my carbon bonded to hydrogen. And I see that that is 413 kilojoules per mole. Okay, so we have 413 kilojoules per mole. And if we consider the number of bonds and we say like a mole of this is going to happen, so we have a mole of these things, well, that's actually 4 moles of these bonds. And so that's where we get this times by 4, okay, times by 4 moles of that bond. And the moles cancel, and you're actually just left with kilojoules. And so we're going to take this. Really, I probably should have drawn my parentheses over here. Okay, so 413, because that's how much energy it takes to break one of those bonds, kilojoules, times it by 4, because we have 4 of those bonds. And then that's not the only bonds that are broken. These ones are also broken. So now I'm going to add that to, okay, this is going to be my double bond, right? So oxygen double bonded to oxygen is 498, so 498 kilojoules. And this is 2 of those double bonds. And that's my reactants. That's all the bonds that I'm going to break for my reactants. So I just did the first part of this, the sum of the bonds being broken. Now I need to minus it from the sum of the bonds being formed, okay? So I'm going to subtract this whole thing. So I'm going to subtract this whole thing. If I had written it smaller, I probably would write it right there, but we have a carbon double bonded to an oxygen. And I look up at that table up above and it says 799 kilojoules per mole. But we're going to multiply this by 2 moles, or 2 times that this bond is broken. And then I'm going to add that to the hydrogen single bonded to oxygen. That is 463 kilojoules per mole, but this happens 4 times, or 4 moles worth of those bonds. And that's all of those. So I'm going to take these numbers, add them together, those numbers, add them together, and then subtract them from each other. You don't have to do it all at once in your calculator, but you can, but just make sure you get the double parentheses. So it's like the bracket and then the parentheses. 413 times by 4 plus 498 times by 2. That's my reactants. I'm going to minus it from my, and really I am saying reactants and it is reactants, but that's the amount of energy it took for the bonds to be broken in the reactants. And then this is the amount of energy that's released when the bonds are formed in the products. 799 times by 2 plus 463 times by 4. Okay. So this is good to see. So we're seeing that our delta H is going to equal negative 802 kilojoules, just like what it was telling us on the diagram on the prior page, that for this reaction, our net in and out overall is going to be losing negative 802 kilojoules to the surroundings. It's exothermic. Delta H for this reaction is negative 802 kilojoules. Okay, so if you sum together, you draw the Lewis dot structure, and you sum together the amount of energy of the bonds broken minus the amount of energy that's released when bonds are formed, that will tell you the delta H of the reaction. Okay, here is the second way of calculating delta H. We're going to save example number 2, and we're going to do that in class together. And now we're going on to topic 6.8, and this is the delta H of formation. Okay, so if you see this little degree symbol, that means standard temperatures, pressure, and pressures. F is formation, and that means that we have 1 mole of something that's being formed from the individual elements. So 1 mole of substance is formed in its standard state from the elements in their standard state. Standard, again, meaning 25 degrees Celsius and 1 atmosphere. Okay, so this delta H of formation is specifically for sulfur trioxide, this SO3. We're forming 1 mole of the sulfur trioxide from the individual elements, sulfur and oxygen. And the delta H when this formation occurred was negative 396 kilojoules. Okay, cool. That's why we have this weird fraction. That, like, don't stress out about that. It just, the reason why is this had to be 1 mole for that. Now, the cool thing is if you look at the formation, these standard enthalpy of formation, for everything in a reaction, we can see what the delta H would be for the entire reaction. Okay? So here it's showing us that the standard formation of nitrogen dioxide, it has a positive, it's endothermic, 33.2 kilojoules. But for sulfur trioxide, that it actually releases energy, it's exothermic. That the elements, when they're all by themselves, has a delta H of formation of 0. So if I were to look at a chemical reaction like H2 plus O2 turns into 2H2O, there's a couple things I'd have to do. First off, it would be the formation of water, but I can't have this be a 2. It's got to be a 1 mole, and so I got to divide everything by 2. So this would become a 1, this becomes a 1, and then that's where we get the weird, like, half. Everything's divided by 2, that becomes a half. And then these have a standard formation of 0. This is their delta H of formation is 0 because they're in their pure elemental form. And we'd run this reaction, we'd see what we'd have over there. And guess what? A whole bunch of chemists have already done this for you. So this is the delta H of formation for H2S from the individual elements. Here's the delta H of formation of like this gaseous hydrofluoric acid, HF. Here's sulfur trioxide, and then, oh, we got 6 of those, so SF6, and that's what we'd get. Now, on the last topic, it was the sum of the amount of energy of bonds broken minus bonds formed. Be so careful because this is different. This is products minus reactants, not the amount of energy of bonds broken minus formed. This is products minus reactants. So if we add together the delta H of formation of all the products, and we add together the delta H of formation for all the reactants, and we subtract products minus reactants, then we can get the delta H of the reaction, which is really cool. So here's my reaction. H2S, there's 1 mole of H2S, there's 4 moles of F2, 2 of HF, and 1 mole of this SF6. So let's look at our products first. So if I want to do my delta H, I'm going to look at my products. And I have 2 moles of HF. So I'm going to take 2 moles, and I'm going to times it by the delta H of formation for the HF. So I'm going to times that by negative 273, and look at the units, kilojoules per mole. Kilojoules per mole. And so again, it's like moles are canceling, okay? So that would be for the 2 moles of HF. Now, I also have 1 mole of SF6. So 1 times by negative 1220 kilojoules. And those are my products, okay? So that's my total amount of products. And now I'm going to subtract it from my reactants. So on the reactants, I have 1 mole of H2S, so times by negative 21 kilojoules per mole. There's the H2S, let's see, SF6, H2S, and I'm going to add that to 4 moles of the F2. Okay, F2 was negative, oh yes, 0. F2. F2 is in its pure elemental form. It's not combined with anything else. And the delta H of formation for anything in its pure elemental form is always 0. So 4 times by 0. So I just don't need to include it in there. Okay, so plugging this in my calculator. Double set of parentheses. 2 moles of HF times by its delta HF formation, 273. And then I'm going to add that to 1 mole times by the formation of SF6, so negative 1220. And then I'm going to take all of those products, I'm going to minus it by the reactants. And I had 1 mole of H2S at negative 21 kilojoules. And 4 moles times by 0, which would just be 4, so I'd be adding that to 0. So my final delta H of this reaction is negative 1,745 kilojoules. Okay, and I need to point something out because sometimes they say kilojoules per mole, and really they mean reaction, moles of the reaction, because this is what would be released exothermic if this reaction happened with those amount of moles reacting. So that's like the kilojoules per reaction, or moles of reaction. Let's do one more to end with. So I have my reactants, I have my products, and I know I'm doing products minus reactants. So my delta H is going to be products. So I'm going to start with that. I have 1 mole of carbon dioxide gas. So I'm going to come to my list here. Here's CO2 gas, and then I see what my delta HF formation is. So I have times by negative 393.5 kilojoules. And I'm going to add that to 2 moles of water liquid. Okay, so 2 moles times by H2O. Notice we have H2O gas and H2O liquid. We're going with the liquid. Negative 285.8 kilojoules. Great. So those are my products. And then I'm going to subtract this. Okay, I'm going to subtract this from my reactants. Okay, and on my reactants, I see I have 1 mole of CH4 gas. CH4 gas right there, negative 74.8 kilojoules. And I would add this to 2 moles of O2, but O2 is in its pure elemental form, so it would be 2 moles times by 0, right? It's not on this list, maybe it O2 times by 0, because any of these that are in their pure elemental form, only that element and nothing else, it would be 0. So anything plus 0 is just itself, so that's why I'm not adding it to the other side there. And then I'll run this number. So negative 393.5 plus 2 times by negative 285.8. Okay, that whole thing minus negative 74.8 because there's only 1 mole of that. So I get a final answer of negative 890.3 kilojoules. Now, when I look at these are technically all added and subtracted. I didn't do this earlier, I should have, but it would be digits after the decimal. So do you see how all of these, besides the moles that we're multiplying, they're 1 digit after the decimal, 1 digit, 1 digit, 1 digit, and so my final answer is going to have 1 digit after the decimal. So that would be my delta H, another exothermic reaction. We kind of saw this here as well, where we didn't have any digits after the decimal, and our final answer does not have any digits after the decimal. Alrighty, everyone. Thank you for your hard work. We'll do this example during class, and then we'll get lots of practice in, because that's mostly what's needed for these topics. It's just doing them over and over, making sure we're understanding, is it energy of bonds broken minus energy of bonds formed, or is it the formation of the products minus the formation of the reactants? Okay, see you all in class next time.